with these because we're literally talking about them in class. Um, so what is a divide and conquer algorithm? It's basically you take a big problem, right? And then you section it off into a bunch of smaller problems. And then you solve those smaller problems and you combine it into the big problem solution. So you can there's a sort of general pseudocode for it that is as follows. You basically have, real quick, I just want to outline there's common steps in every divide and conquer algorithm. You're going to divide the input problem by some factor that is greater than 1, because if you're dividing it by a factor that's less than 1, then that's not very effective at all. You're going to conquer each subproblem, and then you're going to combine the results. So your algorithm, whenever you do divide and conquer, is going to look something along these lines. It's not always going to be exactly the same, but you're going to have sort of a set of your solution, and you're going to have a base case, right? And you're going to check if the input is the base case. And if it is the base case, you're going to brute force the solution, and you're going to get your solution sort of how you would. So for example, in merge sort, right, when you get to your base case, right, that's when you only have one element in the array. And then, hold on real quick, I'm just going to adjust my volume settings. There's just a lot of background noise. So in merge sort, that's where I left off, I think. When you get to the base case, it's going to be when there's one element in the array, right? And that's our base case because that is trivially a sorted array, right? There's no other permutation for an array with one element, so you know it's sorted. So, and then otherwise, right, if it's not the base case, right, you're going to divide it, right, into a bunch of subproblems. In this case, we call them children problems, right? And then for each of the children, right, you're going to solve that subproblem. And oftentimes, right, involving that, solving that subproblem, right, is going to involve calling this, divide and conquer algorithm again on the subproblem. Sometimes it doesn't. Most of the time it does. Probably 99% of the time it does. And the algorithms we talk about today, they do. So you're going to conquer those subproblems, right? And then you're going to combine those into your solution, right? So it says, don't be, confused by the plus equals here, right? It doesn't, you're not always adding, your subproblem into the solution. Sometimes you're merging it in, sometimes you're weaving it in, other times, you're doing like a 76-degree Fourier transform on your subproblems, and then you get a solution from that. It varies across all the problems. So we're going to use these whenever, so obviously it doesn't say so, but whenever it can make your algorithm faster, right? And then when all the following are true, the problem can be divided into its subproblems. The problem and its subproblems can be solved independent of each other. And the solution to the problem can be constructed from the solution to the subproblems. So this basically means that you're going to be able to separate your big problem into a bunch of smaller problems, right? And then the smaller problems have something to do with the solution to the big problem, right? But they can be solved independently of that. So here are some of the common uses for divide and conquer algorithms. These are two we're going to talk about: binary search and merge sort. There's also quick sort, matrix multiplication, exponentiation, a bunch of other things. If you guys are interested in like reading more, I recommend reading about the merge hole or quick hole algorithms, because those are actually pretty cool, but they do require probably like at least a 240 level understanding of computer science. You kind of have to like understand what a graph is and stuff to sort of grasp that. But I do recommend reading about those. We won't be talking about those today, unfortunately. So let's take a moment and talk about merge sort, right? So you guys are probably most likely, you're in, a computer science major maybe, or you've had some exposure to computer science. So you know that a naive implementation of a sorting algorithm is something like bubble sort, insertion sort. Insertion sort sometimes isn't naive, but a lot of the times it is. Selection sort, the list goes on and on. And a lot of the times, right, these will have a average run case And this theta notation, right? It's basically the same as big O notation. Big O notation is based on an upper bound, right? This just means instead of an upper bound, it is the average bound. Or it's a little more nuanced than that, but you can just think about it as being the average bound. So on average, it's going to be proportional to, or the time taken is going to be proportional to n squared, where n squared is the size of the input list. Merge sort, however, is n log n, and it achieves this by a divide and conquer algorithm. So you could look at the merge sort algorithm real quick, and we can identify the steps that make it a divide and conquer algorithm. So here we have our division, right? So we're taking our left and right, and then we're dividing, or sorry, we're not taking this, we're taking our input array, right? And then we're dividing it and putting it in our left and right arrays, right? And then we're sorting it by calling this merge sort again, right? On the left and the right. And then we are merging the left and right together. And sorry, let's go back. There's also an implicit sort of base case to this, right? Where, if the length of A, right, is greater than one, it's just going to, or sorry, if the length of A is less than two, or it's, you know, less than equal to one, either or, it's going to be just the current array, right, which is the array of one element, and it's just going to return that. So you kind of see that it's skipping this whole thing and it's going down. So that's our base case. And real quick, just yeah, y'all don't worry. I'll figure it out. Sad, that was my soup maybe. But so real quick, I just want to show you guys why exactly this is faster, and we're gonna do this by taking this wonderful JPG of a blank white image and drawing over it because somehow my whiteboard isn't working on my computer. So hold on, I just have to check. Can you guys see? No, you cannot. So I think I need to change windows. You guys not see?
We can see the drawing.
You can see, yeah, but I don't think you're able to see when I draw over it. I'm pretty sure. Kind of annoying. Okay, I guess. Yeah, I'm trying to figure out how I change to sharing. Change windows here. There we go. Oh, here we go. Okay. All right, so you guys should see the snip now. Hopefully I don't just X out of. Okay, yeah. So you guys see. There we go. So real quick, I just want to consider that when you have your base case, right? You have N. That is an awful color. Hold on. Get rid of that. Pick something pretty. Better. There we go. All right. So we're going to have our sort of, when you put the array in, right, we're going to have n elements in the array, right? So let's indicate that with this, right? And then we're going to see that when we merge this in, right, we're going to sort of go through all the elements in the subarray, right, that we divide in half, and we're going to push it in. So that takes theta of n time, right? And then when you take this, right, we have this. Actually, we're not actually going to use the theta notation yet because we do want to keep the factors in how long it takes to solve. So here we're going to have n divided by 2, n divided by 2. And then we could see here, right, that when we divide this in half, right, we have n divided by 2 plus n divided by 2 because we're going to be merging our subarrays in, right? So that's going to be another n sort of iterations. And there's an implicit constant factor to this, but we're not going to worry about that. And then as we go down this tree, right, and we get more, we get n divided by 4, n divided by 4, n divided by 4, n divided by 4, right? We get another n, right? So we get n divided by etc. So how far down is this tree going to go? So that's a question. So you guys could just say the answer if you know. So if we continue down and down and down, what's the height of this tree going to be if we keep dividing n by 2? Now remember, once n equals 1, right, we're going to stop going down the tree. So the question I'm asking is sort of how many times can you divide n by 2 until it is a number that is less than 1? Any thoughts?
I was gonna say, is it n times? Or no, because n over n is 1.
Well, no. Let's think about this. So you think
Okay.
you could
I
divide
tried.
it n times, right? But you're dividing it, right? So that would be n. Once you get to your end result, right, you'd be n divided by 2 to the n, right? And if you think about that, that's going to be like a ridiculously small number, or that's going to be very close to 0 or sufficiently large n.
Yeah,
So
I see.
I'm looking more for, say for example, we want to say so maybe you know n equals 2 to the k, right? We wanted to say, what would this k be here, right? If we wanted, to solve for k. Because when you think about it, right, you're going to be your last node, right? Or your last height of the tree is going to be two to the 2 to the k elements in this case for how many times you can divide it, right? Because we double it each time. And it's actually, sorry, that's my, um, so yeah, so somebody said log 2 of n. Did I hear that right? Yeah, that's perfect. Yeah, that's exactly right. So we're going to be, we'll have a height, right, from here up to the top of log 2, right? Or sorry, log of n, log 2 of n, right? That's really awful. Hold on. Right. So we're going to be down here, right? And we could see here, right, that every time we go down, it's just going to be another iteration of n times that we go through the algorithm, right? And we have a height of log 2 of n, right? So how many times, do we have to iterate through sort of the elements of the array, right? If there's a height of log 2 of n and we're iterating through n times at each part of the array. Any thoughts? It's a very simple answer. I mean, if you think you know it, you probably do. Anyone? N log 2. Oh, he's talking in the general chat. I was looking at the questions. N log 2 of n. Nico, you are on fire because that is perfect. So we're actually going to have a runtime, right, for this algorithm, which is approximately n log 2 of n. And the reason for that, right, so is because if we're going down this tree, right, which is sort of this like a recursion tree, and we're going down this, each layer of this tree, and it's only log 2 n times, right? And it's n iterations at each layer of this tree. We're going to have n plus n plus n dot 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 down to n for a height of log 2n, which is essentially just multiplying by log 2n. So we're going to have, and it's actually log 2n plus 1, but we're not going to worry about that for now. And essentially, we're going to have a runtime for this, right, of theta of n log n. So hopefully this sheds some light. I know maybe if you're not as familiar with trees or sort of the math that's being used here, that this might be a little confusing for you. If you have any questions, you're welcome to ask now. But this hopefully sheds some light on why divide and conquer is preferable to sort of the naive implementation. Because the naive implementation, right, would be of n squared, and n squared grows a lot faster than n log n. In fact, I think, if you do the math, right, for like 4 billion, right, sorting 4 billion elements, it's going to be like the difference between, what's a billion? That's like 10 to the 9, right? So that's going to be like 16 times 10 to the 18th calculations versus 10 10 to the 10th calculations. So that's like a ridiculous difference. That's a difference of like basically a billion, 100 million actually. So it's very good to use divide and conquer where it's applicable. All right, we're going to go back to the PowerPoint presentation now. So hopefully I can figure out how to do that. It doesn't take as long as last time. There we go. All right, so you guys can see the presentation?
Yeah.
Okay, good. So now we're going to talk about how do we develop our divide and conquer algorithms. Well, obviously the first part, right? You have to determine if divide and conquer is applicable. So if it is, right? Your first step, you're going to try and figure out how you can take solutions of the smaller problem, right? And combine them into the bigger problem. So in merge sort, right? We figured if we took two sorted arrays, right? We can merge them together in n O of n time, right? Just by sort of inserting the array, the elements of the array in order. Once we figure that out, right, we have to also figure out a base case because divide and conquer is intrinsically linked to recursion, right? And everyone should be familiar with infinite recursion, right? Stack overflow errors, we don't want that. Okay, this is ACM. We're above that. And finally, we have to develop a routine which solves the smaller problems until the base case and combines the result into the larger problem. So this is the actual implementation of the algorithm, and it's the part that's going to combine this all together. So it would be the actual, code you've written and how you ordered that and how you figured that out. So now I'm going to talk about binary search for a little bit. Binary search is actually, I'm kind of cheating you guys because this isn't actually a full divide and conquer algorithm because there is a division and there's a conquering, but there's no combining. However, it is technically a divide and conquer algorithm and it follows the same sort of idea and philosophy. So we want to find the location of an element in a sorted collection of n items. How do we do this? One way we could do it, right? If you're being naive, you just iterate through the array until you find the item, right? And then once you find the item, you return. If you don't find the item, you get to the end of the array, then you return null. Now, the educated way to do this, right, would be with binary search. And how this works, right, is that we basically start with a midpoint in the array, right? And then we look at whether our element that we're searching for is greater than or less than that midpoint. And if it's less than, right, then we only consider the elements that are to the left of that, right? And when I mean to the left, I mean elements that are less than because it's sorted, right? So you have 1, 2, 3, 4, 5, 6, right? We're looking for 2, right? We choose our midpoint at 4. We could see that 2 is to the left of 4 because it's less than 4. We're only going to look at the elements 1, 2, 3. We're also going to, if it's greater, right, we're going to look at the right elements. And the divide and conquer part of this comes from the fact that we could do this sort of recursively until we only get to one element. So you could see here that our base case is if we find the if we find the element, right, mid is going to be the middle point of the array we're looking at, right? We're going to return that element. Otherwise, right, if we have an element that's less than what we're looking at, right, we're going to look at the, well, here I'm pointing at, the side that's for the greater than, but yeah, so let's just say, so if we have an element that's greater than what we're looking at, right, we're going to look at only elements that are to the right of the midpoint we're looking at, right? And if we only have, if we're looking for elements to the left, then we do the same except for the less than elements. And we do this recursively, right, until we only have one element, and then we return that element. And it isn't written here, but there's also another base case where we run out of elements to look at, in which case you just return null. So now that you've learned about this magnificent algorithm, unfortunately, it can't be applied everywhere. And here's when it can't be applied. So first and foremost, if dividing the problem is inefficient, you don't want to use divide and conquer. For example, if you have, I'm trying to think of a real world example, but it's coming off my hand. So hypothetically, right, say you have a problem that you could solve in O of n time, right? Or you could divide it into two subproblems which take O of n time. That's not very efficient at all, actually. You've just doubled the computation time effectively of your algorithm. And by O of n time, I mean it is approximately the same amount of time to solve those subproblems, because obviously if there's some factor you're dividing by, right, you could sum it up and it works out. That's what worked for merge sort. But in this case, right, if you have a poor sort of constant for your division, right, then it's not going to be very effective to use divide and conquer. Another thing, right, if dividing the problem is equivalent to solving the problem naively, just don't do it. For example, if you could do something in a for loop, right, or you could just do like a recursive algorithm that calls something in effectively the same way. I mean, why would you do that? It's probably even slower, to be honest, because now you're messing with the stack and everything. And lastly, when the smaller instances of the problem depend or relate to the larger instances of the problem, then it gets a little trickier to solve, to sort of solve our problem with divide and conquer algorithms. Sometimes you could get around this by using dynamic programming, but for the most part, you're going to want to sort of think of your other options when this is the case. So now here's some example problems that you guys can do for homework. I was thinking about walking through some of them for you, but I'm kind of a little too tired. So I'll just copy those into the chat. There we go. So you guys are welcome to do those on your own time. They're very fun problems, in my opinion, at least. Especially the last one. That one's actually, it's not. I'd hardly call it fun, but it is definitely a good experience to sort of deal with a confusing problem like that. So it's divide and conquer. But the solution uses dynamic programming. Yeah, they're not necessarily different things, but a lot of the time they are. For example, yeah, like you know, I'm pretty sure like top-down approach to dynamic programming is literally just divide and conquer, right? That makes sense, right? Yeah, because top-down, yeah, 'cause you're just separating it in. So yeah, at least for this case, I mean, leak code had it tagged as dynamic programming, and I like the problem. So I had it tagged as divide and conquer, not dynamic programming, and I like the problem, so I figured I would include it. So now I guess I will ask if anyone has any questions. Yes, sir. Mhm. It's also good for well, binary search especially is good to know for interviews, because I've heard that's something that people like to ask. So if no one has any questions, I guess we're done here. Paul, do you have anything you'd like to say before? Hmm?
Hold on. Yeah. Okay, so
All right, thank you.
that was a great presentation.
Good job, Thomas.
I heard you mention.
Thank you,
the term,
Ryan.
all right, I heard you mention the term for loop. Can you elaborate on that?
Uh,
Yeah. What do you mean by that?
sorry,
what is
I
it
didn't
for?
hear your question, but can you say that again?
For loop. You mentioned that.
A for loop, like using recursion to sort of emulate a for loop.
Oh, got you.
Is that what I could show you how you do it if you want. I can just like make another slide.
Oh,
So
you said for loop. I thought
Yeah.
you said something else. Oh, sorry.
Oh, okay. No, you're good.
I said for loop. I'm sorry.
For loop.
I thought you mentioned some new loops.
Oh,
A new
a
loop.
new loop. Yeah.
I was like, wait, this guy inventing loops?
I am known for being very avant-garde in computer science. I loops.
All right. Thanks for clearing that up.
Mhm.